part of the lecture.
Okay. So I will start by remembering you where we arrived the other time in order to study the quantum mechanics with conformal field theory. And if you maybe remember, what we have done was to map the problem of quantum quenches into a slab where we introduced some regulator in the path integral, okay? And basically what we have shown that the quantum quench problem is equivalent, if we buy this analytic continuation, to a slab problem in which here there is the imaginary time tau between 2 points tau 1 and tau q, which at the end of the calculation should be analytically continuous to minus epsilon minus IP and epsilon minus IP. And what we say is that we will assume this tau 1 and tau 2 to be real during the course of the calculation, and only at the end of the calculation perform this analytic continuation. And the operator in the expectation value are inserted in the imaginary time tau equal to 0, all of them. So we are considering equal time correlation. Okay, and we face the problem that the width of this slab actually is 2 epsilon, and in the limit epsilon that goes to 0, the slab disappears, and we would like to interpret this fact and to understand what are the consequences of this. What I have said the other time is that, and that's where we finished actually, that under normalization group flow, we expect that any translational invariant boundary condition flows to one of the possible boundary conformal field theory, which depends on the condition that we pose here, psi naught. Okay, and let's say then that what we should do, we should substitute this psi naught with some psi naught star, which is a boundary conformal state. But what does this mean? Okay, this is a quite known problem in boundary conformal field theory that was actually shown by John Carter back in the 80s, so it's nothing new, but okay, it's probably not so known outside of the community that makes a boundary problem. And the point is, let's imagine we start with a latticizing model where all spin points in direction up. The magnetization per unit length is clearly 1, okay? And this is not a boundary conformal point. The boundary conformal state is the one where you start making normalization group on these, and in any interval there are more and more spins, all pointing in direction up. So the magnetization at the boundary condition of the conformal one actually diverges. Okay? So let's imagine to have an Ising model in a half plane, for example. It's not meeting the second condition, it's the same. So what we are saying is that the physical condition is that the magnetization, let's include magnetization here, getting model, and the boundary is just 1, for example. It means that there is 1 spin per unit length, and this points up. But the conformal boundary condition actually is the one where the fields, where the magnetization diverges from the boundary. How this is understood in conformal boundary condition, in conformal field theory? This is understood with the fact that the conformal boundary condition should not be imposed at 0. Okay, so if this is the x, what you expect the magnetization does. Since the model is at some critical point, magnetization should decay like a power law, going away from the boundaries, because the model is critical and so there is no magnetization there. Okay. But how this matches with the boundary condition that is conformal invariance, the idea is that the boundary conformal condition should not be applied at the origin, but at some distance from the origin. And this distance is called extrapolation length. Side 0. And this extrapolation length takes into account the distance, in quotes, between the actual boundary condition, for example, all the speed up, okay, and the conformal invariant one. Okay? Clearly, if you look, as you should, the system far away from the boundary, that's what boundary conformal theory gives, having like 1 over x plus sine of to some power delta, having this sine of, if x is much larger than sine of, does not affect the physics. So what conformal field theory tells you is that when x is much far from the boundary, it's very far from the boundary. And it's not just x much larger than 1, that it's x much larger than this extrapolation length, okay, then the behavior of this magnetization is given by the conformal design. Very close to the boundary, okay, this is not the case. Okay? So the boundary condition should be applied at some distance from the boundary. This, for example, if we have a semi-infinite Ising model, the very same thing applies also to the case when we have a finite Ising model between two boundary conditions. The profile will be something like that. Okay. So this is the magnetization profile that you expect if the boundary conditions are 1 on both sides, and the boundary conformal field theory should be applied on both sides of the slab at some distance. Sine of. Okay, so this is it's quite intuitive what is going on, and it's something that is understood, as I say, from early 80s. But now, we have to take this into account in our problem here, okay, and then make the continuation and see what happens. Okay? If we take this into account, what we have, so we have started from the problem where it's this one. We have some initial state here and here that plays the role of a boundary state. We want to substitute it with a boundary conformal state, but in order to do so, we should enlarge the strip. Okay, so this is the original strip. We should enlarge the strip of this extrapolation length that just for, since we are in imaginary time, I will call it tau naught. It's the same sign of that before, just tau because it's time now, but it's exactly the same object. And instead of adding this condition to psi 0, we will have psi 0 star which is the conformal invariant boundary condition to which the initial states flow. Okay? And this tau naught is more distant is the actual initial state from a boundary equal to 1. You can imagine, for example, if you are always, it's always good to have in mind the one-dimensionalizing model. If you are relatively close to the critical point, and then you make a quench to the critical point, the states from which you start is very far away from the boundary conformal state. That will be, for example, if you are in the ferromagnetic region, the one that I was plotting here with all the spin up. Okay? If instead you are at zero field, the state is not yet conformal invariant because the magnetization per unit length is still finite, it's not diverging, but it's quite close to it. Okay? Like imagine that the value here is not 1, but is down here. In order to get infinity, you have to extrapolate very far away. So this prediction becomes more and more accurate closer you are to the conformal point. Else there are very important irrelevant terms that you should take into account in some way. Okay, so this is the regime where all what I'm saying is valid. At this point, if we have this tau naught here, the total width of the slit is 2 epsilon plus tau naught. Epsilon from before and tau naught now. But having understood that there is this tau naught, I can now take safely the limit epsilon equals to 0, and the net effect is just to replace epsilon with tau naught. So in the limit epsilon that goes to 0, the width of the slit is 2 tau naught. Okay. And this is finite, and we have an interpretation for this object. Okay. So in this limit, the width of the slit is tau naught. The two boundary points end up in tau 1 equal minus tau naught minus plus or minus IT, and tau 2 ends up in tau naught minus IT. Okay, and at this point, what we call origin of the time does not matter so much, so we can just translate to have simple formula later, everything by this guy in order to start from 0. And if we do so, our final geometry is the following: 0, Q tau naught, and the operator are inserted at tau naught plus IT. Okay, so I added to everything here tau naught plus IT, obtaining 0 instead of 0, tau naught plus IT, and here Q tau naught. Okay, it's just a translation of the origin of the time. And the most important thing, on the boundary, there are these conformal invariant boundary conditions for which we can actually make calculation. If the boundary condition are not conformal invariant, we don't know what to do. Yes.
I suppose you're going to apply conformal theory, but
Yeah.
I understood that conformal theory actually gives the same result as what you want to compute if you are at large distance from the boundary. I mean,
Yes.
much larger than zero.
Yes.
But you are distant to zero at most because it's big.
No, but then I will take this IT that goes to infinity. Yeah, it's a big. This object should be larger. So the distance is in this in the complex plane here that we don't see.
Okay.
No, clearly we are making a linear continuation, so
It's okay.
everything, all the results that we will get should be checked somehow and should be taken with care, not to believe that this is the truth. Okay? In particular, I can anticipate actually, just to be clear, that some physical quantities can depend only on this tau naught, but irrelevant perturbation on the boundary, okay, can affect importantly something. Okay, like for example, we will find out that the large time behavior under this hypothesis seems to be third-path, while from other solution of integral model we know that large time behavior for integral model is always given by a so-called generalized Gibbs ensemble when one takes into account all the integral of motion. But conformal field theory is integrable. Why this happened? Okay? This is a bit more complicated. What happened in this case actually, for particular choice of this boundary state, all the values Lagrange multiplier in this generalized Gibbs ensemble assume exactly the same value. So basically, it's a degeneration of a degenerate GG. If you instead introduce irrelevant of the boundaries, while these don't change some expectation value of very large distance, this object change the value of this Lagrange multiplier, and so the final state will not be eternal. Okay, so it's important for some teams. It's important to take the difference from what I'm saying here, but it's much more complicated. Just to be clear that to anything should be given the proper sense and not more than what they say. Okay. But okay, as a first thing, I would like to show how we can use to calculate this object to calculate the correlation function and entanglement entropy that we have seen. Now exactly the same thing, just the entanglement entropy is the correlation function of some special operator. Okay, so. So if we have this geometry, where we have some operator inserted on the at tau naught plus IT, okay, let's call it tau, and will be real for all our calculation. Only at the end we can continue it. And how we can calculate expectation value in this geometry? As usual, we'll come up with this geometry in something that we know, that in this case is the upper half plane, where we have this sine mode everywhere. And the mapping between this plane, let's call W, and this plane, let's call Z, is given by the usual logarithmic transformation, W equal Q tau naught divided by pi logarithm of W, logarithm of Z obviously, and inverse transformation Z equal E pi W divided by Q tau naught. And under this transformation, you can realize that a fixed time in this geometry just ends up in a fixed angle in this geometry. Very similar to when you make radial quantization. It's the same kind of transformation you use, and equal time commutation translates into fixed time of commutation rule. If you have seen this, else it's not important. And now, under this mapping, we know the correlation function on the plane of the operator. Under this mapping, we have to map back, and now the correlation function transform. I already wrote once, but let me rewrite. The product of a given number of primary fields, phi I, wi, on the strip is equal to the scaling factor of each point, that is the absolute value of the derivative of the transformation, to the minus xi, x is the dimension of the field, times the correlation function of the upper half plane U is states for upper half plane, and in this formula is meant that to have the correlation function in terms of W, you have to make this mapping and then express Z in terms of W according to this formula. Okay? Let's start from a very simple example that is not useful for the entanglement entropy, but is useful to understand. That is the calculation, for example, of a one-point function of some primary operator. So we want to know how a one-point function evolved after this quantum range. So we have only one of these guys. The expectation value of the primary operator on the plane Z, okay, so we have one point Z on the upper plane is just some structure constant which depends on the boundary condition. Let's go to sign off. Let's go keep sign off. No, it depends on the field phi that is here and on the boundary. That means this final star. Divide by, as usual, images method, the distance between the two charges is just imaginary part of Z twice to the scaling dimension of the field phi. Now, if I have a point at some distance r from the origin at time tau, that's what I'm interested, under this conformal mapping, Z of W1, we have only one point, but that's W1, is just E phi R plus IT divided by Q tau naught. Tau here is the imaginary time that only at the end should be continuous, but for the moment we assume it's real. And this makes a very big difference. Okay? Because now we have to take the imaginary part of the Z to plug in here, and this change if tau is real or not. But we assume it's real. That's the important bit. The imaginary part of Z is just e to the pi r divided Q tau naught sine pi tau divided by Q tau naught. Why? The derivative of Z calculating this point is just pi divided by q tau naught times the exponential always. And what we are interested in is this absolute value. Which is pi divided q tau naught into pi r divided by q tau naught. Okay, I repeat because it's important and often people make confusion with this. The analytic continuation entered exactly here. When calculating imaginary part and absolute value, we treat tau as a real number. Okay? We are not allowed here to say tau is equal to tau naught plus it, so it has an imaginary part. Here it's a real number. Okay? Just at the end, after we wrote the full correlation function, we can make the analytic continuation. So if I put together these two bits, the expectation value of correlation function at point r at imaginary time tau on the strip is a phi b divided by. You can see that r dependence cancel because there is this derivative and this guy exactly in the same way, and there is no r dependence, as it should be as a check of our calculation. This object is translational invariance in r but not in tau, so the r dependence cancel. This we are very happy. Okay, and then we have 4 tau naught divided by pi sine pi tau divided by q tau 0 to this power x phi. Notice that when tau naught becomes large, you just go back to the previous result that it should. And just to, before analytically continuing, just for an interpretation of what is happening, this is just saying that the expectation value like of magnetization in this strip is just given by a formula like this, where this shape that before I was just plotting is just 1 over sine. Okay? Just this is something that exists independently of the quenches, and we can understand what that means. Okay, this is just the magnetization profile in a strip where we impose fixed boundary conditions. Okay. These are dependent. Fortunately, drop down as it should. This is the final result. And on this result, now we are allowed to make tau that goes in tau naught plus it. In order to do so, we have that sine, this sine of pi tau divided by q tau naught just become sine pi r plus it pi divided q tau naught. And this is nothing but the cosh of pi t divided by q tau naught.
Why they are not fluid? Because tau wasn't. It was just real.
Yeah, we finished the calculation now. At the end of the calculation, we have to make the analytic continuation. Okay, so at this point, calculation of the observable is finished. You calculate the observable in the slab, and only at this point you make the analytic continuation. Okay, not before. Before you get nonsense. And notice that this will be even more surprising with more complicated formula. When I make the analytic continuation, there is no, when I can continue a random function, there is no reason why something that is positive or it's real, not analytically continuous, remain positive and real when analytically continuous. Okay? This is the fact that this object remains real and is even positive because you have to rise some power. Okay, gives quite some. It's quite a non-trivial statement, and it's. So if you instead of sign you got the cause and you make the analytic continuation, you get something wrong. That makes no sense. So it's not that any function that would have been there would have given a meaningful result. The fact that the final formula that we get for this and for all the other observable makes sense, gives some consistency check at least of whatever we are doing. Okay. Now, so if we replace this inside here, the time dependence of this one-point function is just this a phi b phi divided by 4 tau naught 1 over cosh phi t divided by 2 tau naught, everything to the power minus x phi. But I want to stress.
Cosine, the last formula is
The last formula is
no, cosine should be x.
No. The exponent plus.
no, it's in the.
It's okay.
I put my here. There was no minus here. It's minus.
Ah.
It's that. It's the same thing. So
This is a question. So we started when we had epsilon plus it minus it and minus epsilon minus it. So we played, I mean, we changed everything because we had conformal velocity and add this tau zero. But we will keep that notations in calculation. This will nothing will change. Instead of tau zero, we will have
just that you have epsilon, you don't know what is epsilon. Tau zero, it has a quite clear definition, and as I was saying, it's connected with distance from the boundary point. And for example, just to make an example, if you make a similar equation, a free field theory, that you can make directly in real time without going through this craziness, and you make a quench of the mass, you can say that this tau naught is nothing but the inverse of the initial mass. In the limit where tau naught is small and the initial mass is big, or the initial mass is big. Else it's a complicated function of this guy. Okay? So, but you have an interpretation of this. While epsilon is just epsilon and it remains there. But, again, this formula should not be taken literally because as it's written, does not hold time. This formula is valid only if time is much larger than this tau naught. This was the starting point. So don't pretend that when t goes to 0, even if you get something that makes sense, because it's just 1 and you get this, but this has no interpretation for the quench. This formula is valid only in the limit time much larger than tau naught, where you get this a phi b times pi divided 4 tau 0 is minus x phi times an exponential of minus pi x phi x phi time divided by q tau naught. This is the formula that makes sense. So, and there are several bits of this formula that should be understood and interpreted. First of all, where the initial state is. The distance of the initial state from the boundary boundary conformal point is in tau naught. So the initial state it's a bit in tau naught. But it's not only there, the initial state is also in this amplitude. Like if I start from a boundary condition in Ising just to have something clear that has zero magnetization, this magnetization will not be created by nothing. Okay? But would make this formal divide even in that case just that this amplitude is zero. Like in the slab, if I have 0 here and 0 here, the magnetization will just be 0 everywhere. Okay? So the initial state is in tau naught and in the amplitude in flow. Second, we see an exponential relaxation to 0. 0 that is also the equilibrium value of this field. So from the 1 point function to putting, we are going to equilibrium. As you will see, is not the case. Okay. And the lifetime of the boundary state that can always be defined, it's not universal because it depends on this tau naught. Okay. And this is all the only thing that I want to stress. You can repeat the exercise for a free field theory. It's done, for example, in our papers. And you can see that in the case of free field theory, this formula indeed is correct in the case when you make a quench from very large mass. Okay, so this tau naught plays the role of, so in this very simple case, let's say I start from a free field theory with the action equal mu phi squared plus m naught squared phi squared. Okay, and I change m naught, I say to 0, this is my quench. If this m naught is very large, okay, that is very close to boundary state, then tau naught is proportional to m naught minus 1. Okay, this is just to have an example where all these things go through more or less correct. Okay. I want to leave this plot to calculate a tuple function that will give also the entanglement entropy. Okay, these things probably quite useful. So now we want to calculate a tuple function at one. So we have 2 points here, W1 and W2. W1 equal R1 plus IP, and W2 equal R2 plus I tau. Again, equal time but different points. These two guys goes in a Z1 and Z2 under this conformal mapping. A general 2-point function, as I said the other day, can be obtained by image method. So we have Z1 bar, Z2 bar. If this charge like is plus, minus, minus, plus. Okay, so the general 2-point function in the upper plane, phi of Z1, phi of Z2 is equal, I just copy to avoid error with Coulomb. In the denominator you put opposite charges, that means Z1 Q, Z1 bar Q bar, Z1 1 bar, Z2 Q bar, and on the numerator you put charges with the same sign, that means Z1 Q bar, Z1 bar Q, and this to the dimension of the field that we have called x phi. And we have to multiply this object by an arbitrary function that depends on the field phi of the 4-point ratio. Let's put eta to distinguish it from x that is around all time. And this 4-point ratio eta can be written there are several ways to write the 4-point ratio. And the one I choose is Z1 1 bar, Z2 2 bar, divided by Z1 2 bar, Z2 1 bar. Okay, so this is the general two-point function on the alpha plane of a primary operator, obviously. And now we want to use this conformal mapping to know what we have obtained on the slate. Again, the mapping is that Zi is equal to E pi Ri plus I tau divided by 2 tau naught, that you can divide between real and imaginary part as before, e to the pi plus I divided by 2 times e to the I pi tau divided by 2 tau naught. So let's see the various quantities that enter in this expression. Zi I bar, the distance between one point and these image charges, is just twice in Zi, imaginary part of Zi, and then it's just q sine pi tau naught tau, sorry, by q tau naught times pi Ri divided q tau naught. This is the easy bit. The distance between 1 and 2, Z1q that enter here, is equal to e to the I pi tau divided by q tau naught. Okay, this is not distance, this is just the difference between the cubes. E to the pi R1 divided by q tau naught minus e to the pi R2 divided q tau naught. And so, if I take this product here, Z1q, Z1 bar, q bar, that's nothing but Z1q absolute value squared. Okay. The absolute value of this is 1, and only the square of this other guy is left. E to the pi R1 divided by q tau naught minus e to the pi R2 divided by q tau naught squared. Can sound pedantic, but it's really good to see the calculation, to see also all the possible checks of things, how they are going. The last bit that we need is this numerator. So we have constructed this guy, this two here, we need only this one. So what we need is Z1 minus Z2 bar more absolute value squared. And this clearly you can write as Z1 squared, Z1 bar, I mean, minus Z1 Z2 bar, minus Z1 bar Z2, minus Z2 plus Z2 bar. And if you substitute definition, this is just, let me to take short to not write every time pi 2 tau 0, just let's forget about this normalization. E2 Ri plus E2 R2, these two guys here, minus 2 E R1 plus R2 is 2I tau plus minus 2I tau, where all the distances are expressed in pi divided by 2 tau 0. So I put pi divided 2 tau 0 equal to 1 and we will restore at the end, as I just try a lot of pi and tau 0 with no reason. Now I put these three pieces together to calculate this ratio. Also the derivative in front, and this will give the expectation value on the strip of the two-point function is equal to pi divided q tau naught squared. I don't take here the power, so this is just this ratio. From the derivative I just get e to the r1 times e to the r2. The denominator is written there, e to r1 plus e to r2 minus q r1 plus r2 cos tau. The denominator is e to the r1 minus e to the r2 squared, e to the r1 e to the r2 for sine square tau. Okay, you can see these guys just erase. You can also divide and multiply everything by this to see that actually the form that you have is translation invariance, as it should again. So during the calculation, things are not translation invariant, but at the end the final formula is as it should again. And in fact, this object is just pi by q tau naught squared. This is just cosh r, where r is equal to r1 minus r2, minus cos tau, there is a 2 in both sides that we in front, divide by 8, sinh square of r, divide by q, sine square tau. Now it's the time to restore the pi and tau 0. So the real two-point function, pi r1 t tau, pi r2 tau on the strip is equal to, okay, here everything is to the power x pi. Pi divided by q tau naught squared, cosh pi r divided q tau naught. Okay, let's not lose too much time since we are a bit late. Let's make directly the linear continuation because the cos just goes in cosh and sine goes in cosh squared. So cosh pi r divided q tau naught plus cosh of pi t divided q tau naught. Again, everything is real and positive as it should. Sinh square pi r divided q tau naught cosh square pi t divided to tau naught to the power xv. And there is the 4-point function, this function of the 4-point ratio f, that we will take into account in a second. But let's see first. So this is the general expression. Okay. That, as I have already said, for the 1-point function, is valid only as long as t is much larger than tau naught, but also r is much larger than tau naught. Okay, so let's take this limit. So the limit both r and t much larger than tau naught. And what we get? Okay, we get the prefactor I divided 2 tau naught power qx pi. But here there is the most interesting bit now. This cosh becomes just the exponential. Okay, so exponential of pi r divided 2 tau naught. These are the cosh also. But you're thinking me. This is sorry, I was a bit quick here. There should not be this q here because there was a q. Okay, so there is no q here. So and down we have e to the pi r divided 2 tau naught times e to the pi divided by tau naught all to the power x pi. But again, this formula is true only for r much larger than tau naught. So what is this guy? This is proportional to, if r over 2 is much larger than t, actually is larger than t, not much larger, since both of these guys are much larger than tau naught, there is an exponential which a much larger exponent that then we just completely suppress the second. So in the case r divided by 2 larger than t, this guy completely win on this guy that we can ignore, and then in the ratio this and this go away, and just we are left with e to the minus pi t divided by tau naught. In the opposite case, r divided by 2 is smaller than t. This is much larger than this. This 1 on pi, this erased with this, and we are just left with e to the minus pi r divided by q tau naught. So notice a few bits here. First of all, this is just the square of the 1-point function for last time that we derived before. We have pi t divided 2 tau naught before. This means that if the 2 points are separated by a distance, okay, remember here that t is always measured in unit of velocity that we set to 1. So if 2 points are separated by a distance for which the information could not travel from one point to the other, okay, after the time that has passed, the 2-point function of the 2 should be just the product of the 1-point function. You cannot know that something happened. And this is manifesting this way. Okay. Oppositely, after you pass this horizon, the correlation function immediately saturates to an exponential value. So just to give, we will go back to this f in a second, because in some cases it's important. But let's, yes, here there is always the x pi, yeah? Novembre. Everything is on xy. So if I plot the logarithm of the two-point function as function of time, there is a horizon time t star equal r divided by q, and the correlation function, the k exponential, that means the logarithm scale is just line, where the 2 points basically go independently. At some time they realize to be connected by, they fall inside the light code, and then they saturate to that line. We will give a better explanation why this happens like this in a second. Okay, maybe after the break. But before the break, I would like to discuss just the effect of this function f that we, for the moment, we ignored. Okay, then we make some questions and then the break. The function is a function of beta that we say is equal to z1 1 bar, z2 2 bar, divided by z1 2 bar, z1 bar 2. If we put the dependence on this guy on time, what we get here is 2 sinh square of pi t divided by q pi naught divided by the two that being the same, cosh pi r divided by q tau naught minus cosh plus cosh pi t divided by q tau naught. And when you take the limit again of time much larger than tau naught, you get e to the t divided by tau naught. Okay, here there was not. And this cosh square, so it is q is okay. E to the pi r divided q tau naught plus e to the pi t divided by tau naught. And you see now that when this guy is much larger than this, okay, let's make the opposite. When this guy is much larger than this, you just get 1. So if t is larger than r divided by q, you just get 1. If t is much smaller than r over 2, you get pi divided tau naught t minus r over 2. But t is smaller than r over 2. So this guy is very small. It's much smaller than 1. So of this function, we don't need to know all of it. That in the general case would be just impossible. We need just value for 1 and very close to 0. F of 1 by normalization usually is 1. It's just the normalization when the 2 points are very far apart. And okay, we can decide to normalize to 1, or it's just a constant, it's not very important. F of eta much smaller than 1 is the behavior of the 2-point function when 2 points get very close to the boundary, and these are known to define a critical exponent eta, a critical exponent of the boundary xb, that has also a very important property, that when the expectation value of the field on the boundary is different from 0, then xb is equal to 0. So this object again is just a constant. And actually, the proportionality constant here is exactly the e to the phi d squared that we defined before. Okay. So of all this function, as you see, does not change much this behavior, just to normalize some exponent when it does, because in the most interesting case, when the initial value of the operator is different from 0, just does not make anything, because this xb is equal to 0. Okay, and in the other cases, it just change a bit the result. Okay, I think we should make the break because I went very. I used too much more than my time. Yeah, as usually, I will maybe make a bit shorter later because it was too long. And if you want to think some questions, we can start the second hour with some questions from you, so that you have 2 seconds to realize what was going on. Okay.
The x5
The x5 is just the exponent, the same one that was appearing in the one-point function.
Yeah, but there we also didn't have it, right?
Yeah, we added an expression. No, x5 is a number that depends on the depends on phi. Like if you have the magnetization getting more than this 1/8. Okay, it's just a number. It depends on the observable and on the theory.
I see. It's not like the weight of this field or something like that.
It's the scale dimension of the phase.
So it's the same as in the
Yeah.
Repulse boundary.
Yes.
Okay.
That's the trick of the using the charges to forget about the boundary. The only news of the boundary is this xb. That depends actually. This is an x5, it's an exponent that depends on the boundary and on the field. Okay? But the bad behavior, what this formula is saying is that far away from the boundary, you need to recover the behavior in the plane. Okay, if you have the upper plane, you have 2 points and you send this point far away, but they have distance finite, you have to recover the behavior in the back, that's x5. Okay, so the news only come when these 2 points get close to the boundary. This is x5b.
Sorry, also I have a question. I didn't understand why you can use this image trick. Why this works?
Trick work you can see in the Coulomb gas formalities of the formal field theory, because basically this object is like Coulomb gas with some scaling. Okay, so just basically for the Coulomb gas in 2D we'll have a potential at this log. This correlation function we are calculating actually just the exponential of these fields that interact through a log, and the prefactor in front of the log is exactly the dimension of the field. So it's if you have to go to Coulomb gas on study. I don't have time to see. But there is a formulation of conformal field theory in the Coulomb gas formalism where you see each 2 points are nothing but 2 particles that interact on the log, that's the Coulomb potential in 2D, and then everything works for the fields of the Coulomb gas, the primary fields are just exponential of this field. Okay, and then the log, e to the log, makes just a positive. Okay? So I told these things of conformal field theory, but more or less no. This is the idea then, to know why there is a Coulomb gas. This will take another 5 hours. Other questions?
So does it mean that these calculations very far away from the boundary, and your makes sense far away from the boundary? Because if you close to the boundary, you don't know.
No, you have another exponent xb5. The approximation is distances and tau much larger than tau naught. This should be always true. So even distance from the boundary should be tau naught, larger than tau naught. But this is just an ultraviolet cutoff. Then in absolute value, the distance to boundary can be whatever. Okay, you have an ultraviolet cutoff, you should be farther away from that, like I was telling. This idea here, this formula that you get is just true. Far from distance much larger than tau naught, And this is the assumption. And this remains on. When you map to whatever, distance should be larger than tau naught. This remains always true, but apart from data. So. There are other questions? If not, we now build everything that we need to calculate case of most interest for this course, that's the entanglement entropy. Okay, so we want to calculate the entanglement entropy in this quench protocol. And we don't have to make much actually, because the entanglement entropy was a 2-point function of particular Swiss fields that transform my primary operator. So instead of putting, we can use this formula here, and ask this x phi to be c over 12 n minus 1 over n, and we get the results for the entanglement entropy. Let's do that. I don't erase that formula because we use. So the 2-point function of Swiss field between 2 points are 1 and R2, and distance R1 minus R2 equal L. Just to conform to the notation of before, it's the R that we had. In this formula, this object we say is just raised of rho a to the n. Okay. So, if we plug in our results, what we get is Cn tilde, the constant boundary of the theory that we introduced, pi over q tau naught to the q xn, where xn is c over 12 n minus 1 over n, the scaling dimension of the twist field that we discussed already in the first lecture. And then we have this ratio that we can copy in pi L divided by q tau naught plus pi t divided by tau naught divided by the product of the same two guys. Everything to the power cube xn. No, only one xn. So, if we take the derivative with respect to n and we set n equal to 1, we got the entanglement entropy, which is from this bit just c over 3 log tau naught, okay, plus pi ct divided 6 tau naught for t smaller than L divided by Q, and pi CL divided to L tau naught for time larger than L divided by Q. So as you can see, the entanglement entropy has a constant piece that is just the entropy in the initial state. But if you remember, in a massive field theory, we say that the entanglement entropy was just C over 3 log of the inverse of the massive. So this bit is completely compatible with the fact that for very small time we end up in a theory where tau naught takes the whole of the inverse mass. Okay? And then the entanglement entropy, if we plot it, it grows linearly with time, and at time t star equal L divided by Q, it just saturates one constant. A constant which is extensive, which is exactly the same result that we would have a very high temperature, okay, at an effective temperature if you compare with the formula at final temperature, heat effective equals 4,000. Okay, so what we get from this formula is that the entanglement entropy starts from a value that is not extensive. It's constant because does not scale with L. Then it grows linear in time up to the horizon, and then saturates to a value that is a finite temperature value. So it's like the theory for a very long time is at finite temperature. Okay. And in this sense, it says that system thermalizes to temperature that is given by the excess of energy that there is in the state. As I already said before, and I repeat, even if I cannot go through this part now, this is true only for this very specific initial condition. Boundary irrelevant operator on the initial state will change this object and not letting you have a conformal idea. Okay? And not having you a finite temperature. Actually, how the boundary irrelevant operator changed this result, it's a work unpublished by John Cardy, and you can find the slides of this talk that was done here at GGI 1 year and a half ago. Okay, and the paper is still not published. But still, the calculation is there and can be found in these slides. I want now to spend some time in the physical interpretation of this formula and try to understand what changed when we change something, like we released the CFT, what we mean by CFT in this formula. And this will come all from a very simple physical interpretation. So, physical interpretation. Physical interpretation is in real time, not imaginary time. So just to understand what happened in real time, we have this initial state psi naught. And let's imagine time goes in this direction. The initial state has an excess of energy, a very large excess of energy compared to the ground state of the theory. It means quasi-particle excitation theory, whatever they are, like in a free theory are just a real particle, will be produced everywhere in this system. Okay, so it's like something like that. Quasi-particle excitation are emitted from the system, and since we are in the regime in which tau naught is small in some sense, that means the correlation length of the initial state is small. That means mass is very large. It says that we are just looking to observable in this sense. Only particles emitted from the very same point or in a region around psi naught that is very small knows about each other. If the correlation length is like as big as this, you can imagine that a particle emitted here, a couple of particles emitted here, a couple of particles emitted there, they don't know about that, just like a sun. So, and actually in the limit where this is really zero, okay, only particle emitted from the very same point carries correlation and entanglement, and all the other just ignore each other. Then, in a conformal field theory, in a CFT, all the particles travel with the speed of light. So, all the particles travel with the same speed. That we set equal to 1 in our calculation, okay? Because usually the speed of light set to 1. If we want to interpret these results for a real physical system like the Asim model, the speed of the light is substituted by the speed of the sound, okay, which will be a dimensional full number that has something, okay, same speed, let's say it's v. So the formula here should be corrected with v every time there is a speed. So it's vt that has the same dimension of the distance. And it should. Okay, so this is the peculiarity of the conformal theory. There is only one velocity, all excitation travel with that velocity by Lorentz coefficient invariance. And this is not true in a real system, and I will discuss all this change in a second. But then, if all the particles travel with the same speed, you can see that if I look at the system at a given time t after the quench, the distance traveled by the particle emitted by the same point is just qvt. It means that this particle emitted here at this time t entangled the two points at distance qvt before it entangled points at smaller distance. But the calculation here is done by fixing L on subsystem, so like fixing on top of this plot, let's imagine we have this distance L, and we want to know the entanglement between this part of the system and the rest of the system. To the entanglement of this part, we contribute all the particles that emitted from any point at some time. One is inside and one is inside, outside L. Okay? Like at this time, this part, this one, at the time here, this particle is inside, this particle is outside. So this particle is contributing to the entanglement between these two, while the cone that was here, they are both outside L, so they are not contributing to the entanglement. Okay? And even can happen that at a given time, particle goes out of the cone, like there is, in this case, let's imagine it's like this. Okay? This particle was entangling, actually it was the one central is never entangling because it was or both inside or both outside, but there are particles that enter and exit from this. Now, if all the particles travel at the same speed as it is in conformal theory, and we will modify this assumption soon to understand what happens in the most general case, what you have is that for short time before the particle symmetric here goes out of the cone, just the particle living close to the distance L divided by 2 from the boundary entering the path A and start entangling A with B. Okay? And this will be linear because as time passes, more and more particles enter here and the other is outside. Okay, so the number of particles that enter is just linear with the time. Until what time? Until the first particle that enters, that is the one that goes to the boundary, go out. And after that, for each particle that enters, there is one that exits. So the entanglement separates. Okay? And that time is exactly equal to Vt divided by 2. Okay? So, in general, this formula can be explained just in terms of particles that emitted from any point. One goes in A and one goes in B. Counting this particle will be proportional to the entanglement. But if we understood this, we can try to see what happens when not all the particles travel at the same speed. Because also for a system that in equilibrium is described by conformal invariance, this means in general, if we have a dispersion relation that gives the energy in terms of the momentum. For very small momentum, this is linear. But then at some point, this will bend, make something else, like for latticizing model, just cosine, just sine, sorry. Okay? So the velocity is 1 here, which is the maximum, and then becomes smaller, up to going to 0 at the boundary of Brillouin zone, that in proper unit is pi, but this is another story. But so the dispersion, even for a system which in equilibrium is described by conformal invariant, we don't have an exactly linear dispersion relation. We have a dispersion relation that is bending. What is the effect of this bending? Okay? And this is from why we don't have really a theory to make conformal mapping, etc., to make this, because there is no conformal invariance. On the basis of this argument, we can draw some conclusion from the entanglement. And the conclusion actually are very simple. The entanglement entropy between a part A of distance, a part A and a part B will just be equal to, according to this argument, the integral of all the points belonging to A, all the points belonging to B, okay, of the particles which are emitted from any point plus infinity, of the probability that particles with opposite momentum pi are emitted. This is just a number that we don't know, that will give rise to the factor that we don't know. dp times the fact that the particle emitted in x reached x prime after a time t. Okay, so there is a particle emitted in x that reaches x prime after a time t, and this depends on p. Now, and the other particle should reach b. So x second minus x minus dt. So this formula is very easy. Let's summarize. We are saying that particles that are emitted at any point between minus infinity and plus infinity, they start at x. Okay, so one goes in one direction, one goes in another direction. Sorry. So one goes in one direction, and so x prime should be equal to minus pt, and the second should be x second plus pt. So again, just now we are allowing that from each point, not only one particle with speed v is emitted, but particle with several speeds, depending on the momentum. Now, if A is a slit, an interval of length L, I can write this formula in the following way. I write first and then we discuss with be very easy. QT integral in dp fp So I just impose that x is an interval between 0 and L, for example, and if x second is the rest. So the integral of the delta just gives some theta function of the same arguments that can be written in this form because you have to count all the particles with positive and negative velocity going in one and the other direction. Okay. And now you see that there is this velocity depending on the momentum. But first of all, if the velocity does not depend on momentum, so this Vt is just V, we can just carry out the integral over the momentum, okay, because there is no dependence on the momentum apart from this integral that will be a constant, and you will get exactly the same behavior that this theta, one theta is 0 in one case, one theta is 1, it's theta of the opposite argument, so when 1 is 0, 1 is 1, and vice versa, so we will get exactly this behavior of the entanglement into theta linear and then separates. Okay? In the case when, that's what we are interested in, this velocity depends on the momentum, there is always a maximum velocity. Let's say, for example, for a conformal invariant, for a theory that in equilibrium is described by conformal field theory, will be the velocity in 0, which is the maximum, and then everything is smaller. Then, all the other velocities are smaller than the first. So, as long as the 1 theta is 0, okay, for the fastest particle, will be 0 also for the slower one. Particle cannot travel faster than light, let's say. So, independently of the dispersion relation for time, let's try. For time smaller than for V max, time t smaller than L divided by Q, only the first integral, the first integral will contribute to things of this theta is 0 for every particle. Okay? And so we will have always a linear dependence on time. So this is the entanglement entropy for T smaller than L divided by Q V max is always linear. But now, for T larger than this L divided by Q V max, this object is not 0 anymore. And so there is a tail proportional to L. This object is 0 for the largest velocity, but it's not 0 for the slowest particle. That means in that plot, in this plot that I had before, okay, if these are the 2 points of the slits, okay, the first particle arrives first, but later on there will be slower particle that will arrive later. Okay? And tangling or correlating exactly the same points. Okay, so this integral then will not be 0, and there will be a residual time dependence given by this object, and in particular, the behavior for large time will be driven by the slowest particles, because all the particles are getting in and not making anything anymore, and in the end, just the particle with really 0 velocity will arrive at the end, or velocity very close to 0. Okay? And in general, you expect like something like that. Instead of a perfect saturation, you expect a nonlinear dispersion relation to make an entanglement entropy that path like this, so exactly linear up to some point, and then much slower growth due to slower particles. Okay? And in fact, if you take like the one-dimensionalizing model and you solve exactly it, you find for the entanglement entropy exactly this kind of behavior. And when indeed you can even characterize the approach here that something like e to minus 3 half due to the particle with slower velocity. Okay? Okay, this ends more or less what I wanted to tell you today. We are in time. Do you have any questions? This is particularly simple when it's understood. Maybe it can sound complicated. So if you have some questions, please ask. Oh yeah, just then, while maybe you think of some question, I just want to stress, so the linear behavior for time smaller than something given the maximum velocity and dimension of sleep is a general thing of any system, and actually can be shown to be true even in higher dimension. This is just, okay, geometry can play a much more important role, but because you can have a strange shaped geometry, but the linear behavior for short time is true even in higher dimension, like for example some calculation also based on the SCFT explicitly recover. And this will be true even if you take a completely wrong model. It's just causality. If your model is causal, you will get a linear behavior for short time. Okay, so there is nothing to do with CFT. CFT here was very important to understand how things were going, and then starting from something, let's say, solid, you can generalize to a much more general situation. Okay? While the behavior of correlation function is much more complicated in general. You always expect a light cone, something happens at this very special time, but if things really go down exponentially or things like that, this is completely, it depends on the initial state, depends on everything. It's just the entanglement entropy that really just counts the number of particles and does not depend on the details of what is going on. Correlation function should have an horizon effect. This has been measured even experimentally. Okay, so it's not just something in our dreams. There's a very nice experiment in the group of Immanuel Bloch in Munich where they measured the light cone spreading of correlation, as they call, but the shapes that they found is completely different from the one that I showed before, because it depends on the observable, on the model, on everything. Things that show a very universal behavior is exactly this entanglement entropy. That puts it also on a more general grounded other correlation. Okay, so if there are no questions, no? You are all hungry? Okay, then see you on Friday.
Just a